Okay, so in this video, I just wanted to shed a little more light on the relationship between the Laplace transform and the Fourier transform. Okay, so we've been working with the Fourier transform a lot, and what exactly more is the Laplace transform doing for us? Okay, so that's what I want to try and explain here. Okay, and also just their general relationship. So we know the Laplace transform of a signal x of t at a point S, and usually we'll use sigma plus j omega okay, so S is just a complex number. It has a real part sigma, an imaginary part omega, and that omega is chosen to try and remind us of the Fourier transform omega. Okay, they're going to be very related, as we'll see in a second. So the Laplace transform of x of t at that point is, well, it's x of S, which is just x of sigma plus j omega. And we know the Laplace transform is this integral, x of t, and then it's e to the negative st. So I'm just going to plug in s right now. Okay, and now let me just rearrange this slightly and write it as x of t e to the negative sigma t e to the negative j omega t dt. Okay, now what does this look like? Well, if I just kind of underline those two terms together, okay, this should look exactly like a Fourier transform, and it is. This is the Fourier transform. Fourier transform of what signal? Well, now it's x of t times e to the negative sigma t. Okay, it's not x of t anymore, but it's the Fourier transform of that signal at the point omega. Right, so this is just the Fourier transform. If I said take the Fourier transform of this function, right, what would you do? You do the integral of that function times e to the negative j omega t, and that would be the Fourier transform at omega. Okay, so this is the relationship between the Laplace transform and the Fourier transform. In the previous video, we said, okay, what if sigma is 0? What if sigma is 0? If sigma is 0, then we just get the Fourier transform of x of t at omega. Okay, so when I have my Laplace transform, that sigma is 0, in other words, x of j omega, that is exactly our Fourier transform. But this is what's happening more generally. This is the more general relationship between Laplace and Fourier. Okay, the Laplace transform, let me just summarize what that relationship is. So the Laplace transform, well, the precise relationship is right here, but this is going to be sort of a more overview. The Laplace transform, what does it really do? It allows us to add a factor of e to the negative sigma t to our original signal x of t, right? And then take the Fourier transform of that resulting signal. Okay, so what good is that? Well, as we've already been kind of seeing in the previous video, this term can help us achieve convergence, okay? Convergence where the Fourier transform fails. Okay, so we already saw one example of that, okay, in the last video. So if I wanted to take the Fourier transform of x of t, I might not be able to. That integral might not converge. If I get rid of this factor here, that's the Fourier transform of x of t, it might not converge. That integral might just go to infinity. Okay, but with the Laplace transform, it's more general. It allows you to add this factor in so that, hey, maybe now that I have x of t times this factor here, e to the negative sigma t, maybe now I can get this integral to converge. Okay, and all of the points S, all of these points sigma plus j omega, where this integral does converge, again, that's what we call the region of convergence for the Laplace transform. Okay, so without this factor here, maybe the Fourier transform x of t doesn't converge, but when I add that factor in, maybe now I can get convergence. Okay, and that's kind of some of the intuition behind why a lot of our regions of convergence, actually all of them, are only going to depend on the real part of S. Okay, if I draw my complex plane here, turns out all the regions of convergence are just going to depend on the real part of S. Okay, just this axis, the real part of S, whether it's greater than or less than some values. And this is kind of telling us a little bit why, because that part of the Laplace transform is what really is influencing the convergence of this integral. Okay, so this is just kind of some overview to get some intuition for what the Laplace transform is really doing. Okay, and so what does this allow us to do? Well, the Laplace transform is more general, so I'll just write it here. We can take the Laplace transform of many more functions than we can take the Fourier transform of. Okay, so by allowing us to add this extra term in here, that's what the Laplace transform does for us. Now we can get this integral to converge for many more functions x of t than we could without this factor, which again was just the Fourier transform. Okay, when sigma is 0, I literally get the Fourier transform right there. Okay. All right, so let's just apply this sort of high-level logic to an example we've seen to confirm that it agrees with the region of convergence we found before. So let's just think about from the previous video. Okay, let's consider this function we looked at, x of t, e to the t, u of t. Okay, so what does that look like? Well, it looks something like this. Okay, it's just an increasing exponential. Okay, and it increases very quickly, e to the t. Okay, and what did we see? We saw that the Fourier transform does not converge. Okay, so the Fourier transform doesn't exist for this function. Not converge. Okay, and why was that? That was because the function gets too large as t goes to infinity. Okay, it's increasing too quickly. It gets too big. Okay, so we saw when we tried to take the Fourier transform, we did not get convergence. Okay, that's what we did in the previous video. But then we tried to take the Laplace transform, and we were able to. We actually did it for a more general function than just this, but then we applied it to this function. So we can use, just kind of using our logic from earlier in this video, we can use the e to the negative sigma t term in the Laplace transform to sort of limit the growth, or as I like to say sometimes, knock it down, knock this function down. This function's growing too quickly. We need to knock it down with something. So we're going to limit the growth of this function. And this is what the Laplace transform does, right? The Laplace transform is the Fourier transform of x of t times that factor. So let me just write that down. We have e to the t u of t, e to the negative sigma t, and this is just e to the t 1 minus sigma times u of t. Okay, and now this is, we're looking at the Laplace transform with this sigma as the real part of s, and we saw up here that that's really the Fourier transform of that entire function that I just wrote down at omega. So really, we're trying to get the Fourier transform of this function to converge. In other words, the Laplace transform of this function, where the real part is sigma. The real part of s is sigma. Okay, so to get the Fourier transform of this to converge, okay, which again is what we're really doing here, the Laplace transform with that real part of s equals sigma. Okay, now we're taking the Fourier transform of this resulting function. We need the exponential to be decreasing. Right? We need it to be decreasing. Otherwise, the same logic will apply. As long as this exponential is increasing, it's growing too fast. We need it to look something like this, right? Some decaying exponential. Then we know we can take the Fourier transform of that function. We've done it. We did it in the last video. Okay, or we've seen it before anyway. So we need the exponential to be decreasing to get convergence, i.e., what does it mean for an exponential to be decreasing? It means this thing multiplying the t is negative. So we need 1 minus sigma to be negative. In other words, we need 1 less than sigma, which again was the real part of s. Okay, so this is just kind of thinking through, knowing what we know about Fourier transforms of exponential functions, thinking through in the context of Laplace transforms, right? With this understanding that the Laplace transform at sigma plus j omega is really the Fourier transform of this function at omega. So we're just changing our function by multiplying it by this exponential, okay, and then taking the Fourier transform. And with that understanding and knowing what functions the Fourier transform converges for, decaying exponentials, we can see that we need this factor up here to be negative. Okay, so that's just a summary. And so this would get us convergence. That's our ROC. So this region of convergence of real part of S greater than 1, believe it or not, that's the same region of convergence we found by doing all of the math. Okay, so before we did it kind of just algebraically going through the Laplace transform. Now we've done it kind of high level using our understanding of the relationship between Laplace and Fourier, and we get the same ROC. So this ROC here for e to the t u of t is, or I should say for the Laplace transform of e to the t u of t, okay, is the same ROC we derived in the previous video. I'll just say before, or I'll say in the previous video. Okay, so hopefully this kind of demystifies the Laplace transform a little bit. Just to summarize one more time, the Laplace transform at this point S, sigma plus j omega, is just the Fourier transform of a changed function, x of t times now e to the negative sigma t at omega. Okay, so the Laplace transform allows us to add this factor in to try and manipulate this function x of t so that now its Fourier transform can actually converge. Okay, so you get to add in this factor with Laplace to try and get that integral, that Fourier transform integral to converge. And then we kind of talk through, knowing what we know about Fourier transforms, that we need this exponential to be decreasing in order to get the Fourier transform to converge. We're able to kind of reason through what the region of convergence should be based on looking at this exponential. And it's really what we did algebraically. This is just sort of a higher level version. Really what we did in the last video. It's the same idea. But maybe this will kind of help shed some light on the actual relationship between Laplace and Fourier. So in the end, we got the same region of convergence we got before. Okay, so that's all I really wanted to try and just, point that out to you guys in this video. And that's all I had for right now. I'll see you in the next video.